Today, we want to learn about the ratio and root tests. That is 5.6. In the ratio test, we will think about the ratio, the limit of the ratio of the consecutive terms. If limit n goes to infinity, absolute value of an plus 1 over an is L, and that turned out to be 1, less than 1, then the series defined by that sequence is absolutely convergent. Absolutely convergent also means the given series n equals 1 to infinity, an is convergent. The second statement is if limit n goes to infinity, absolute value of an plus 1 over an is L, and that is greater than 1, or the limit n goes to infinity, absolute value of an plus 1 over an is infinity, then summation n equals 1 to infinity, an is divergent. The third one is if limit n goes to infinity, absolute value of an plus 1 over an equals 1, then the ratio test is inconclusive. The first condition definitely tell us that when we think about the ratio, the limit of the ratio, when that is greater than less than 1, then that means the sequence decreases, but that is stronger than the sequence decreases. For example, if you think about the harmonic series, when you apply this ratio test, the ratio of the consecutive term will approach 1 instead of strictly becoming less than 1. So when the sequence satisfies the ratio test, the speed of decay of the sequence will be faster than just decreasing, and fast enough to make the series converges. Let's do some example. Determine whether the series is absolutely convergent. Divergent, or inconclusive. The first problem is n equals 1 to infinity, negative 1 to the n power times 3 to the n power over 2n factorial. The defining sequence for this series is negative 1 to the n power times 3 to the n power over 2n factorial. We think about the ratio, so we consider limit n goes to infinity, an plus 1 over an. This can be written as limit n goes to infinity, absolute value of an plus 1 times 1 over an. If you look at the given sequence, then the given sequence is a fraction form. When we write this ratio as multiplication form, that is a lot easier to calculate. So that is limit n goes to infinity. So negative 1 to the n plus 1 power times 3 to the n plus 1 over 2 times n plus 1 factorial times 1 over n, that is reciprocal. So 2n factorial over negative 1 to the n power times 3 to the n power. So limit n goes to infinity. We forget this negative stuff because there is an absolute value and everything is positive. So we just forget the absolute value sign also. We combine the similar factors. So we write 3 to the n plus 1 and 3 to the n together. And then this one, the next one is factorial, 2n factorial over 2 times n plus 1 factorial. Three to the n plus 1 over 3 to the n power is 3 to the n times 3 over 3 to the n power. So that is 3. So these two cancel each other. And then 2n factorial over 2 times n plus 1 factorial. And so this one can be written as 2n factorial over 2n plus 2 factorial equals this one is 2n times 2n minus 1 2 times 1. And then this the denominator is 2n plus 2 times 2n plus 1 times 2n times 2n minus 1 2 times 1. The numerator and this portion of the denominator will cancel each other, and the denominator is 2n plus 2. times 2n plus 1. So we can rewrite this limit as limit n goes to infinity. This part turned out to be 3. So 3 times the second part turned out to be 1 over this one. So 1 over 2n plus 2 times 2n plus 1. So the this one will be just n goes to infinity. This denominator will grow indefinitely. Therefore, the fraction will converge to 0. So that is absolute convergent. By ratio test. The second problem is summation n equals 1 to infinity n factorial to the 9th power over 3n factorial. So defining sequence is an equals n factorial to the 9th power over 3n factorial. So limit n goes to infinity, an plus 1 over an. So limit n goes to infinity, an plus 1 times 1 over an. So we can write that as limit n goes to infinity, an plus 1. So n plus 1 factorial to the 9th power over 3 times n plus 1 factorial times 1 over n is, so we flip it, then 3n factorial over n factorial to the 9th power. Obviously, none of the factors are positive number. None of the factors are negative numbers. So we don't have to continue to use absolute value. And as we have been doing, we will put the similar looking factors together. So both have 9th power. So let's raise to the 9th power, and fraction goes like n plus 1 factorial over n factorial times the next one is 3n factorial over 3 times n plus 1 factorial. So we don't have to use absolute value. Limit n goes to infinity. What is this? The first part is n plus 1 times n minus 1, 2 times 1 over n times n minus 1 times 2 times 1. So the next one is 3n times 3n minus 1, 2 times 1. And then this part can be written as 3n plus 3. So that is 3n plus 3 times 3n plus 2 times 3n plus 1 times 3n, and then the same thing will go on up to n, up to 1. So these two will cancel each other. And for the first part, these two will cancel each other. And we have to raise that to the 9th power. So it becomes limit n goes to infinity, n plus 1 to the 9th power times 1 over 3n plus 3 times 3n plus 2 times 3n plus 1. If you rewrite, then it becomes limit n goes to infinity, n plus 1 to the 9th power over 3n plus 3 times 3n plus 2 times 3n plus 1. Then we have to determine whether this diverges or converges to a certain number. To do that, we have to compare the degree first. The degree of the numerator is 9, and degree of the denominator is 3. So degree 9 is strictly greater than degree 3. Therefore, the numerator's degree is larger. That means the limit diverges. So the series diverges. The next test we have to learn today is about the root test. Let me state the statement. If limit n goes to infinity, n through the absolute value of an converges to a certain number, which is less than 1, then the given series is absolutely convergent. So n equals 1 to infinity, an is absolutely convergent. Absolute convergent implies the series converges. The second one is if limit n goes to infinity, n through the absolute value of an equals L, then if that is greater than 1 or it diverges, then the summation n equals 1 to infinity, an is divergent. That is obvious because that means the sequence will grow. So we can apply the test for divergence. The next one is if limit n goes to infinity, n through the absolute value of an equals to 1, then the root test is inconclusive. determine whether the series is convergent, divergent, or inconclusive. The first problem is n equals 1 to infinity, -1 to the n power times 4 to the n power over 4n factorial. The defining sequence is an equals -1 to the n power times 4 to the n power over 4n factorial. If you look at the sequence, then there is 4 to the n power. So if we apply the nth root, then we can eliminate this nth power here, and then the things will become a lot simpler to determine the convergence. So we will use the root test. Nth root of absolute value of an equals limit n goes to infinity 4 to the n power over 4n factorial to the 1 over n power so limit n goes to infinity, that becomes 4 to the n power. We can apply this power to the numerator and denominator. So 4 to the n power to the 1 over n power over 4n factorial to the 1 over n power. So that becomes limit n goes to infinity. So these two will multiply together. So 4 over 4n factorial to the 1 over n power. And then we realize that this one is a fixed number, but this one will grow as n goes to infinity. So the denominator will grow indefinitely. That means limit will approach 0. That is less than 1. Therefore, by the root test, that converges absolutely. The second problem is n equals 1 to infinity, n to the 13th power over e to the n power. The defining sequence is an equals n to the 13th power over e to the n power. Then limit n goes to infinity, nth root of absolute value of an equals limit n goes to infinity. An is n to the 13th power over e to the n power, but we have to put 1 over n power because we are applying the root test. From here, we can multiply the power here. Then that becomes 1. So we just think about the limit n goes to infinity n to the 13th power over e. Then that will grow indefinitely. This time that is located on the numerator, so that becomes infinity. So the series diverges. The third problem is summation n equals 2 to infinity, negative 3n over n plus 1 to the 3n power. Again, there is a fraction and power has 3 times n power. So if we take a nth root, then the power will become simpler. So we use root test. The defining sequence is negative 3n over n plus 1 to the 3n power. Then limit n goes to infinity, nth root of absolute value of an equals limit n goes to infinity, absolute value of negative 3n over n plus 1 to the 3n to the 1 over n power. So we apply the root test and n times 1 over n power. So limit will cancel each other, becomes 1. So limit n goes to infinity, it becomes absolute value of negative 3n over n plus 1 cubed. So we can forget the absolute value sign by dropping negative sign in front of 3, and this is cubed. And so this one can be written as 3 cubed times n over n plus 1 cubed by applying that one here and that one here. So we will write that 3 cubed times n over n plus 1 cubed. So this part will converge 1, and the remaining one is this one. So that is 27, which is greater than 1. Therefore, the series diverges. Five 5.6 was a short section. The next section is about the power series and functions. 6.1, power series and functions. Power series looks like this: n equals 0 to infinity, Cn x to the n power. When we write further details, it goes like C0 plus C1x plus C2x squared plus, and then that is a power series. Here, what you have to be careful is Cn is so-called coefficient. So that is a fixed number. Those may be different, but those are fixed number. But x is a variable. We are considering a series, but it is not just a one series because x is a variable. Therefore, when we change it to x value, the new series will be created. So we are considering the collection of power series, the collection of series which are infinitely many, and think about the behavior, convergent behavior. Summation n equals 1 to infinity, Cn times x minus a to the n power. Instead of x, we can multiply by x minus a to the n power. And then we can rewrite that as C0 plus C1 times x minus a plus C2 times x minus a squared plus da da da. In this case, this is also called a power series in x minus a this time, or we call it as power series centered at a, or that is power series about a. When we just say that is a power series without talking about center, you can just assume that we are talking about the power series centered at 0. So this one. Before we go further, it is important to know what is power series, what is not. So summation x to the 2n plus 5 over 9n plus 4 factorial. Then this can be written as summation n equals 0 to infinity 1 over 9n plus 4 factorial times x to the 2n plus 5. If you look at the power, then you realize that power doesn't go like the x squared, x cubed, and so on, because power is formulated as 2n plus 5. So when the certain power terms are vanishing, we can consider the coefficient is 0. What is important here is this is a variable to this certain power, and this is a fixed number which depend only on the term. So this is a power series with Cn equals 1 over 9n plus 4 factorial. And that power series is centered at x equals 0 because nothing appears there. The next one is summation n equals 0 to infinity x to the 2n over sine of 3x this is not power series. Why is that? Because this can be written as summation n equals 0 to infinity 1 over sine of 3x times x to the 2n. These two are looking very similar in the sense x to the certain power is multiplied to a fraction. But unfortunately, in this case, x is also a variable. Instead of n, we wrote x here. So this cannot be a coefficient. The next series is n equals 1 to infinity, natural log of 9n times x plus 9 to the n power over negative 9 to the n power. Then we can see that this is x minus something, the variable to a certain power. And then when we look at the remaining part, we have to see whether the remaining part contains any variable. The answer is no, because those are n. So those are qualified to be coefficient of in the power series. So this one is power series centered at x equals negative 9. So be careful, the center is not 9. You think about x plus 9 equals 0 and then solve it, then that is x equals negative 9. So that is power series centered at x equals negative 9 with the coefficient Cn equals natural log of 9n over negative 9 to the n power. I will continue with 6.1 tomorrow.